institute as Cuong. He's by Vietnamese. One should call him Cuong, the last name. Doan Trung is a family name, but Cuong is a name. But in Vietnam, the name is most important, officially and unofficially, friendly. So we call him always by Cuong. So Cuong, he graduated at Hanoi University of Science in 2003, and thanks to his excellent record during the bachelor, he was admitted to the PhD program immediately, and in 2007 he completed his PhD under the supervision of Nguyen Tư Cuong, so another member of our institute and a close friend of Ngô Việt Trung. Right after the PhD, he got the postdoc position at Duisburg Asian University, which under the supervision of Ellen Esno. After that, he came back to the institute, to our institute, and a member of our institute since there. But when the Vietnam Institute for Advanced Study in Mathematics was founded, he got another 2 year postdoc 2 year. And since 2 years ago, he became the deputy director of our institute. So his topic is his interest is a local cohomology module, in particular sequentially conmorphic module and multiplication. And recently, he also worked on the degree of projective variety jointly with Cuong from VCAS, Korea. So today he will talk about his work with Cuong. So please.
Okay, thank you very much for the introduction, and I would like to thank Professor Verma for the invitation to talk in the seminar. It's very nice that we have some way to communicate. And today I would like to talk about my recent joint work with Professor Cuong from KAIST on Betti number and ideal structure positive subscheme of almost maximal degree. So in my talk, so my talk will consist of 3 parts. First, I will explain what I mean by subscheme of almost maximal degree, and then I will talk about the Betti number, Betti table of the subscheme, and the last part I will talk about the ideal structure. So let me start with the first part. I'd like to talk about upper bound, so for the degree of subschemes. So for projective subschemes, there are several bounds have been known for the degree. So I think the most famous bound is lower bound by the codimension +1. And there are also some upper bounds in terms of codimension or the Castel-Newport-Mumford regularity. So today I would like to talk about an upper bound in terms of reduction number. So let me remark about the definition of reduction number. So we will work over a field over an infinite field, and I denote by x0 the polynomial rings in variable x0 to xn plus e, and let R be a quotient of x0, which is a standard graded K algebra, and I assume that the dimension of R is n. Then by Norton normalization lemma, we can choose a linear form y1 to yn, such as the R is a finitely generated module over the polynomial rings in variable y1 to yn. Now let's B1 to Bs be a minimal set of homogeneous generator of R. Here we consider R as an S module. Then the reduction number of R with respect to S is defined like this. So this is a much more generating degree where we want to be as run over own minimal set of generator. And the reduction number of R is defined if we take the minimal value of own reduction number and S run over own natural normalizations, then we get the number and we call it the reduction number of R. Now I change a little bit to the language of variety and scheme. So let X be a non-degenerate projective subscheme of codimension E. And I denote by Ix, the saturated ideal defining X, and Rx, the homogeneous coordinate rings of this subscheme. And here I assume that by changing the variable, I can assume that this polynomial ring in terms of xe to xn plus e is a neutral normalization of so here it should be Rx, so the coordinate ring of X, such that the reduction number equal to the reduction of R with respect to X. So if we can consider R as a module over X, then it is generated by monomial in X0 to Xe minus 1 of degree at most R, because R is upper bound. I mean the maximum degree in a set of generator, then we have the following bounds. So this is the number of monomial in terms of x0 to xe minus 1 of degree at most R. So this one is bigger equal to the minimal number of generator of R over X. So it's bigger equal to the degree of X. This upper bound is our starting point. We will consider the case when the degree equal to this upper bound or almost equal to this upper bound. Usually in commutative algebra, when we have some bounds and equality occurs, then we can then the algebra or the variety must be good. So also in our case, it's also the case, and I will explain in more detail later. In literature, there are some other bounds, as I mentioned from beginning. So if X is a variety of codimension E, then the degree of X is bounded by this upper bound in terms of the codimension and the regularity. There are also famous lower bounds by the codimension plus 1. So when the degree equal to the E plus 1, then X is called a minimal variety of minimal degree. So classification of the variety was established in the 19th and 20th centuries by the work of D'Ampezzo, Betti, Harris, and also studied by Eisenberg and some other people. And the next case is when the degree equal to E plus 2, X is called of almost minimal degree. So the variety has been studied by Vogel, Stuttgart, Hoa, Prassmann, Sense, Park, and other people. Especially in 15 years, there are many work by Prassmann and Sense and their collaborator on the variety, and they got many interesting properties. So we will consider when come back to our upper bounds. We will consider when the upper bound is attained or almost attained, and we try to compute the Betti diagram of the variety, and also to obtain other property. Now I'd like to come back to the reduction number and explain the relation between the reduction number with other numerical invariant of the algebra. So we consider the minimal free S0 resolution of R. So here I want to remind that S0 is a polynomial rings in terms of x0 to xn plus e. And R is similar to the homogeneous coordinate rings. Here the index of the Betti number is a little bit different from other author. So we denote it by beta ij for our convenience. And with its notation, we have the Betti table. So this is the Betti table of R. And in this Betti table, the Castelnuovo-Mumford reality is concerns the size, I mean the number of rows, and the positive dimension concerns the number of columns of the table. And so with the Betti number, in many situations we are interested in the vanishing of the Betti number. And if many Betti number vanish, then it can imply many properties of the algebra. One of the properties is the NTP property. This was studied by Eisenberg-Koto and Eisenberg, Green, Hulek, and Popescu. We say that R satisfies the NTP property if the Betti number finishes in this corner. So in here I put the red corner. So this is D. D is 0 and P is a column. And if the Betti in this corner finishes, and we say that R satisfies the NTP property. Relation between the reduction number and other, there are several relations between the reduction number and other invariant of the algebra. I would like to mention some relation with local cohomology. So here we denote by AI to be the top index, such that the local local cohomology, the I local cohomology is non-zero, and so the regularity of R is a maximum of AI plus I for any i's. In 2000s, in 1986, Trung has several work on the reduction number, and he found this bound. So the reduction number is bound by the regularity above and by the an plus n below. Here n is a dimension of the algebra. So in the case of coherent algebra, then the regularity equal to an plus n, because other local commutative vanish. So we have the equality between the reaction number and regularity and an plus n. When the algebra satisfies the NDE property, we also find some another upper bound for the reaction number. So in this case, the reaction number is bounded by d minus 1. So, and and there are some works to study the case when the reaction number equal to the regularity. But in fact, there are many examples showing that the reaction number can be much less than the regularity, and also the d number. D here is in the NDE property, and here is codimensions. For example, the example by Ulrich, the famous example by Ulrich, we consider the polynomial ring in 4 variables, and I is ideal like this, and here T is any number equal to 2. And in this case, the polynomial rings in terms of x2 to x3 is a not a normalization of R. And the Betti table of R is like this. We can compute it. So in this case, the regularity must be T, while the reduction number is 1, because because S is a natural normalization, so R is generated over S by 1, x0, and x1, so the reduction number is 1. And also in this case, the algebra satisfies the NT plus 1, 2 property, but not the NT2 property. So in this case, in this example, this number and this number are the same, but this number is much smaller. The reduction number is much smaller. So somehow, if we compare the upper bound for the degree, then the upper bound in terms of the reduction number is better, and in some cases much better. Now I go to the second part of my talk. So I will consider the case when the upper bound is attained first, and then almost attained. So I recall some notation from the first part. So we consider positive subscheme, non-degenerate. Non-degenerate means that the subscheme is not contained in any hyperplane. And here we assume that the polynomial rings in terms of xe to xn plus e is a natural normalization of R of the same reaction number, and we will denote it by R. Then the degree bound, since it is a degree bound, so the degree of x is bounded above by R plus E choose E. And when the degree equal to this bound, then we say that the subscheme has much more degree. I recall that when the homogeneous coordinate ring is coherent, then we say that the subscheme is arithmetically coherent, and I will denote by ACE for short. The first results describing the Betti table is this theorem. So we have the following equivalent statement. The subscheme has maximal degree if and only if it is arithmetically coherent with an R linear minimal free resolutions. It means that the Betti table has its shapes. It has here is beta 0, so it's LOA 1, but other place are 0 except this position. So this the R strength in the table. And it's in this case we can compute precisely the Betti number. This result was proved in 2017 by An, Han, and Kwak, and they assume under the assumption that the characteristic of K is 0 and X satisfies the N R plus 1 E property. And in our work, we move on the assumption, and we have this final statement. Using this theorem, we can obtain some property of variety with small reduction number. Small reduction number means that's reduction number equal to 1, 2. So the first consequence is this one. So here, projective variety means that irreducible, reduced subscheme. So for any projective variety, the degree is so here should be Rx is low is about below by the codimension plus 1, and when the equality occurs, then we say that the variety is minimal. Here means that of minimal degree. Then we have the following equivalent statements for projective variety. So the reduction number is 1 if and only if the rarity is 2 and if the X is minimal. So somehow the new part is the reduction number is 1 if and only if the rarity is 2. So for this we apply this theorem because because the degree is bounded below by E plus 1, and when bounded above by this number, and when R is 1, then two numbers are the same. So the degree must be equal to E plus 1. The second case we consider is when the reduction number equal to 2. Is this case is very complicated, and we cannot compute the Betti table of X in own case. We must assume that the variety is arithmetically coherent. In that case, we can describe the Betti table like this, and we give the relation between the Betti number by this, for example, beta 1, 2 with beta 2, 2, 1, and so on. Example of such subvariety is there are several examples of subvariety. So here is example in study in Hua's paper in 1993. So X is a 10 peso variety. And Hua was able to compute the Betti table with a precise Betti number. In this case, the reduction number is 2, and it also satisfies the N3E property. Now I go to the next case when it's an almost maximal case. So it means that the upper bound is almost a shift. It means that the degree equal to the upper bound minus 1. Is it so? When the degree equal to the upper bound, then we have seen that the variety must be ACM. But when it's almost maximal degrees and it's not the case anymore, it can be non-ACM. So first we consider the ACM case. So if X is subscheme of is ACM subscheme, then it has almost maximal degree even if the ideal defining ideal can be described like this. So the other degree E is the degree R apart is only one dimension vector space, and for higher it's had linear resolutions. So somehow we can describe the idea of this subscheme quite clearly. Using this, we can describe the Betti number of the of these subschemes. First, we have some example. So the example showing that this case happened. In fact, so let's see the smooth curve of degree phi and zenith 2. So I take this example from Hassel's book. So in a paper in of Naito in 2002, he shows that this curve is ACM, and he computes the reduction number of this curve. Actually, he compute the Norton normalization, and we can show that the reduction number is 2 from his result. So in this case, because the degree is 5, so the curve has almost maximal degree, and this is a Betti table of the curve. Another example is Castanevo surface. So if X is a Castanevo surface, and it is a smooth, it is smooth and ACM, and the degree is 5. And in this case, S0 resolution of this surface is described like this. And we can show that K2, K2, 3, 4, the polynomial rings in terms of X2, X3, X3, X4 is a Norton normalization of R. And we have this isomorphism. So because of this, we we can see that the reduction number of X is 2, and because the degree is 5, and the codimension is 2, then X has almost maximal degree. So this is another example of almost maximal degree, which is ACM. Now we have a description of the Betti table. So suppose X is ACM subscheme, then it has almost maximal degree even only if the Betti table has this shape. So it have 3 strands. This one, and other plate are 0. And the Betti number beta IR satisfies the formula. So we can compute precisely the Betti number. Now we go to the next case, the almost maximal case, which is non-ACM. This is the most complicated case. So in this case, the coordinate ring is no more coherent plane, so everything is must be much more complicated. So the key results is its part is its theorem 13. So let X be a positive variety of almost maximum degree, then we can show that the depth of Rx is bigger or equal to the dimension of X. So if the depth equal to the dimension of X plus 1, it's ACM. And so and the remaining case is when the depth equal to the dimension of X. So it's somehow the almost coherent matrix. I have no time to present the proof of this theorem. There are some key in the proof. First, because X is variety, so here I emphasize on the variety assumptions. Then if we take a reduced group basis, then it contains irreducible polynomials. And using the group basis, we are able to describe explicitly the initial ideal of the defining ideal of X. And then we saw that the positive dimension of Rx is equal to the positive dimension of S0 over the initial ideal. So from this we apply this inequality. Using this and also the description of the initial ideal of then we okay. So we have the two remarks. The first remark is the conclusion of this theorem is not true if we consider subscheme instead of variety. And as I mentioned, if X is not ACM, then we have the equality between the depth and the dimensions of X. Then using this theorem 13, we can describe quite precisely the initial ideal of the defining of X. So assume that X is a variety of almost maximal degree, and we with it we keep it assumption. So that S is a natural normalizations with direction number R. Then we have the following equivalent statement. X is almost okay. So here I'm sorry. I should remove these assumptions. X is so the equivalent statement are the following: X is of almost maximal degree and not ACM. If and only if the initial ideal of the defining ideal is related by monomial of degree R plus 1 in X0 to E minus 1, and a monomial UV where U is a monomial in X0 to E minus 1 of degree R, and V is a monomial in the remaining variable. So we can so we have a very quite precise description of the initial idea. And if we consider the coordinate ring as an S modules, then the graded Betti number has can be computed precisely like this formula. And and for this, the C is in fact it's not very difficult to imply C, but C is very important because we have some mapping cone sequence which relates a Betti number of to say Noether normalizations and the usual Betti number. And this is now we come to the description of the Betti number in this case. So suppose X is a variety of almost maximal degree, and assume that X is non-ACM. Then the Betti table of X has the following descriptions. So the first case, when the regularity of the coordinate ring is equal to the reduction number, then here I would like to remind that the regularity is always bigger or equal to the reduction number. So when they equal to each other, then the Betti table has only two strains. So the second one, we can compute the Betti number precisely by this formula. The second case is when the regularity equal to the reduction number plus 1. In this case, the Betti table have three strains. And in this case, we cannot compute precisely the Betti number. We can only have a relation between the Betti number. And the last case, when the regularity bigger than the reduction number plus 1. In this case, the Betti table is similar to the second case. But fortunately, we can compute the Betti number precisely. So this is formula for the Betti number in this case. And because of the first and the third case, which I many times we spend quite a lot of time to compute the Betti number in the second case. For example, we can expect that beta I are equal to this one, and beta I minus 1 are plus 1 equal to this one. So it's similar to the last one, but we was not successful. Later I will explain why. Okay, so now we have a three case, and it's natural to ask whether we have the, I mean, whether they happen in nature, in fact. It means that whether we can find example who whose Betti table have this shape, then I go to some example. Example for the first case. So in this case, I take a smooth curve degree phi and genus 1 in Hasson's books. So this is an example I took, but it's different from the previous one. So in Naito paper in 2002, he computes the regularity of this. Actually, he computes the minimal resolution of this curve. And he implies that the regularity equal to 3 and C1 is not ACM. And we can show that the reduction number of this curve is 2. And because the degree is 5, so it has an almost maximal degree. And this is a Betti table of this curve. The second example. So this is for B. So if we take the rational curve defined by this map from P1 to P3, then this had degree phi and 0. This is a rational curve. And the Betti table is like this. This curve is not ACM, and we can show that the reaction number is 2, and so it has almost maximal degree. And the last example is for the case C. So, so in this case, I consider a rational curve genus 2 if defined by this formula. And in this case, the Betti table is like this, and the reaction number is 2. So the degree is 9. So it's also almost maximal degree. And I must say that to find this example, we have to do Macaulay 2. So it means that we have the safe. I mean, in the theorem, we okay. I'd like to go back to the theorem. So in the theorem, we have this this table and we have the descriptions, so, and we try to do Macaulay 2 to find whether we can find some rational curve who I mean we because the theorem, so we have this Betti table from beginning, and then we do Macaulay 2 to find whether we can find some rational curve who satisfied it. Then luckily we were successful. So I think without Macaulay 2, for us it's impossible for us to find that example. Now I go to the last part about the ideal structure, and I will discuss about the K2 in the last theorem. So this case, and I will explain why we cannot compute the Betti number precisely. So it the component Y linearity plays some role in this part. So this is second case in the last theorem. So here I remind that we can have only the relation between the Betti number. I would like to remind about the definition of component Y linear ideal. So let I be a homogeneous ideal in S0. We denote for any number D, we denote by ID, the ideal generated by degree T part of I. Then Herzog and Hibby defines it defines. I mean, Herzog and Hibby they gave the definition of component Y linear ideal. They say that I had a component Y linear resolution if the degree T part had a linear resolution for only. So any ID part. And they say that if I is linear, then it is component Y linear. And they also say that prove that a Stanley Reisner ideal is component Y linear if and only if the Alexander dual is sequentially coherent. This notion of sequentially coherent is a generalization of coherent rings from the unmixed case to the general case. It means that for ring with associated prime of different dimensions. And this notion of sequential coherent was given by Stene and Peter Sensei independently, as I know. In fact, there are many examples of monomial ideal with component Y linear resolutions. But there are not so many. There are not so many examples of works on prime ideal with component Y linear resolutions. Here I mentioned some works. First one by Francisco Miglior and Nagin. They characterize tetrahedron curve with component Y linear resolutions. And later Nagin study curve with maximal Hasson-Rao modules. And he shows that they are, on most of them, are also component Y linear. In a joint seminar between Japan and Vietnam in Hue in 2018, when I talk about our work, Satoshi Murai has asked me a question whether variety of almost maximal degree component Y linear. At that time, I could not answer him, but later I discussed with Sejong Kwak, and we found that component Y linearity is very good for us to understand the second case in the theorem 15. So so but not only in this case, I I would like to consider this property component Y linearity for all the case from beginning. So if X has a maximal degree, then then X has a linear resolutions. So so in this case, component Y linearity and linearity are the same. I'm sorry, I mean, how to say? So in this case, the variety is very special. It's a very special case of component Y linearity. In theorem 9, if X has an almost maximal degree, and if it is ACM, then the degree, so here R is the reduction number, then the dimension of this degree is 1, and the other degree has a linear resolution. So in this case, the ideal also has component Y linear resolutions. This is the ACM case. And how about the non-ACM case? For the non-ACM case, we have the following theorems. So let X be a variety. So in this case, we have to consider a variety of almost maximal degree. Then the defining ideal of X has a component Y linear resolution if and only if. So here we are able to give if and only if condition for component Y linearity of X. First, the regularity equal to R. So this corresponding to the KR in the theorem 15. And second is the regularity equal to the reduction number plus 1, and the Betti number equal to 1. In this case, we need one more assumptions, and the regularity equal to the reduction number plus 2. So this corresponding to the KC in theorem 15. And X does not have a component Y linear resolution if and only if the regularity equal to R plus 1 and the Betti number equal to 0. This explains why we in theorem 15 we cannot be precise formula for the Betti number in the second case where the regularity equal to reduction number plus 1. We are able to give example to illustrate this case, but but before that I would like to give an application to give a Betti table. So in the almost maximal for almost maximal variety, the remain K2 we could not give a precise Betti table is when the regularity equal to R plus 1. So if we assume that the Betti number beta 1 R plus 1 equal to 1, then so this case corresponding to in the previous theorem. So this is this case. So with this assumption, the defining ideal is component Y linear. So and then we are able to describe the Betti table precisely like this. And here the Betti number has this formula. So it's as our predictions. And this is an example. So in this example, we have to do Macmillan 2 also. And we find a rational curve with this formula. And in this case, the curve have a reduction number 3, and the degree is 9. So the curve is almost maximal degree. And this is a Betti table. And in this case, I'm sorry. I'm sorry. The example showing that this case appear is the previous example we mentioned to illustrate the case B. And this example is for the remaining. So in this case, the Betti number is 0. Beta 1, 4 is 0. And by this theorem, so this corresponding to this case, then by the theorem, then this curve is not component Y linear. This is a summary about the component Y linearity and our description of Betti table. So the maximal case, the variety is ACM and it's linear, and we are able to describe explicitly the Betti table. The second case also is a component Y linear. So the third case is almost maximal degree and non-ACM. In this case, it's a component Y linear, and we are able to describe explicitly the Betti table. And using the component Y linearity, we are able to describe the Betti table in this case. So the almost maximal case, non-ACM, regularity equal to R plus 1, and the Betti number equal to 1. So it's a component Y linear variety. And the last one, is almost maximal non-ACM variety, so that's the regularity equal to the reduction number plus 1, and the Betti number equal to 0. In this case, it's non-ACF and it's not component-wise linear. And in this case, we have no precise description of the Betti table. And in this case, I believe that it could be, if we try to describe the Betti table, then we have to divide into many subcases. This is my finish. So I finished my talk here. Thank you.
So thank you, Cuong. Now it's time for question on antimatter. So any, yeah. Please.
Hello, Watanabe.
Yeah.
Thank you very much for your very nice talk. And do you have some example of almost maximal degree with R normal?
Do you hear, Cuong?
Yeah, right now I have no example because I didn't consider that property. So
yeah.
I have no example. I'm sorry.
Okay. Thank you very much.
Other question? I have a question. When it is almost maximum degree and the scheme is not arithmetic column, it is still generalized column or not?
I must say that I don't know. I did try to show that it is bootstrap.
Okay.
And when I follow this this question, I was able to show that it's a canonical cohomoclase. It by this notion was defined by Peter Sense, and it means that the dual of the top local composite is cohomoclase. I mean, the canonical module is cohomoclase. Yeah, that's all I can say about it.
Cuong, I have a question. This is Jugal.
Please.
Yeah. So if you assume your projective variety is smooth, then what can you say about the maximal degree or almost maximal degree? Can we compute the Betti table quickly?
I'm sorry, I cannot hear it precisely.
If the variety is smooth,
Yes.
then does it have effect on the Betti table? If the variety is of maximal degree or almost maximal degree?
Yeah, it's very interesting questions. I think I and Professor Sejong Kwak discussed several times about the relation between the Betti number and the singularity of the variety, but unfortunately we have no information about this. No. So to answer the question, I have no information. I'm sorry.
Okay. Thank you.
In the case of the almost maximum degree, how big is could be custom movement for regularity?
Yeah, it's also very interesting, very interesting question. So here I come back to our terms. So we have a 3 case. Yeah. We have 3 cases. So one is the relative equal to real number. The second case, relative equal to real number plus 1. And at the last one, we was able to describe the Betti table, and we can give some example, but we do not have many example. And how? So in this case, how the relative and the real number depend on each other is also not clear to us. Yeah, I guess that there should be some relation. I mean, something like we can expect to about the relative in terms of real number, but we do not have a better predictions.
Okay.
Yeah.
Any other question or remark? So if not, then I would like to, in name of participant, to thank the speaker and thank the organizer.
Thank you. Thank you very much.
Thank you very much.
Oh, thank you all for your participation.
Thank you. Thank you, Hoa.
So, bye-bye.
Bye.